Yingheng is traveling for another conference. He wanted to present here, but it just so happened that the other conference has exactly the same day and it's in LA, so he cannot make it. So I'm presenting on behalf of him and also Andy, because this µMAG code package was built as a team effort with the microelectronics sub team within CCSE and AMReX team, and also our materials and device experts. So µMAG is a high-performance GPU-enabled data-driven micromagnetic solver for Spintronic system. Understand that this talk and the next one, which is my own talk, they're both very far away from what people were talking about today, because we care about this microelectronic system. We care about how electronic devices and materials are functioning and how we can model that using AMReX-based code package. So let me give you some background here, why we care about micromagnetic modeling and how it is related to the electronic application, right? So this is a workshop report from the 2018 DOE microelectronics workshop. And within this report, it identified several key research directions which are still valid nowadays, that there's a huge challenge in energy consumption in computing. So based on the traditional transistors and von Neumann architecture, the current generation of HPC will soon face a challenge, an energy challenge. So if we don't do anything, then by the year of 2030, it's projected that the computing microelectronics will consume more than a quarter of the global energy consumption. So that's a lot. So there's an urgent need for us to lower the energy consumption of new microelectronics, especially for computing application. So that's why we came here and see if there's any new device mechanism that we can build using new type of functional materials, and spintronic or magnetic materials are one of the very promising candidates. So we use magnetic or spintronic interchangeably because they're really referring to the same type of material, which are governed by this equation called LOG equation. I will show the equation on the next page. This type of material works based on the switch of its internal spin status. So it gives us high-speed operation, and because it doesn't rely on the physical transport of electrons, so the electron doesn't have to move physically from one location to the other, it can also help us to miniaturize the device size, because with spin, you can just rely on the local change of the spin status instead of the non-local electron movement. That's why it gives us the miniaturization of the device size. So to model this device, we have to look into how we solve LOG equation and how is LOG equation coupled with other type of PDEs in the system. So here we build the µMAG feature. Sorry, I promise I will show you LOG equation on the next page, but this doesn't show it yet. So let me just quickly show you how the equation looks like, and then we will come back to the feature slide. This is the equation that we're trying to solve. It looks like an ODE to start with, right? Because you can only see this time derivative of m, and then we have some curl between m and h. They're all vector fields, and then some curl products between many components. But really, this is a PDE, because effective h is a function of m, and effective h can be spatial derivative or it can be spatial integral of m. So here we're really dealing with a PDE that involves m, which is the magnetization, and other type of physics, which could be the electromagnetic physics or the static version of the electromagnetics, or other type of materials, for example, ferroelectric material that can be right next to the magnetic material. So H effective is really the bad player here. It can give us a lot more complicated physics than how it shows here. But if we look into this equation more closely, right, this is the time change of m. And then the first term is a torque term. And we all know that the curl product of two vectors is perpendicular to both of these two vectors. So this is really just a torque which causes m to precess along the direction that's perpendicular to m, right? So if we look at this figure, it's like a pendulum in 3D. This is our m vector pointing to one direction, and m cross h is perpendicular to both m and also the precession direction. So that's the first term. The second term, m cross h. So we know that this term, m cross h, is perpendicular to m and h, and the curl of m with this torque term is, of course, perpendicular to both. So that means that the second term will be perpendicular the second term of LG equation will be pointing to the radius direction. So this is the trajectory of our precession, and then if you connect the tip of m to the origin of the circle, this is the direction of the second term. It is pointing into the origin, and it is trying to pull m back to the steady state. So we call this the damping term because it is really trying to ruin the precision, right? It is trying to pull m back to a steady state. So okay, so this is the structure of the PDE we're trying to solve. It's simple just by looking at the mathematical, but it could be quite complicated because of H effective. So like I mentioned, H effective can be quite complicated. It can be decomposed into different components, and it involves complicated physics. The first could be the bias field. Basically, the user would put an electromagnet or a permanent magnet right next to our material, and then the magnet would apply a magnetic field onto the material. So with the H bias, we have the Zeeman coupling, and it is nothing more than just a known bias field that is defined by the user. The demagnetization field, on the other hand, is the worst of the bad player H effective. It's basically a Green's function if we look at it in this way, but really it's an solution of the open boundary Poisson equation. So what we're trying to solve here is a Poisson equation that is describing the magnetostatic physics of magnetic field, but then the boundary condition is open. We only have H reduced to 0 when we're far enough from the material, right? It doesn't have a very well-defined boundary condition. That's why we end up having this Green's function, which is the kernel calculation. And if we use the regular method to solve the Poisson equation, it's going to be very, very complicated and time-consuming. So for now, we're just use FFT-based linear convolution method, and this is how everyone else does in the micromagnetic community. But still, FFT could be much slower than other stencil calculations, like the anisotropy exchange and DMI, which are described by this stencil calculations here. So those three terms plus the Zeeman or the bias are are pretty fast in terms of the stencil calculation, but the FFT for the demagnetization could be quite slow. So we build MagNex solver with the following feature. It's, of course, based on AMReX. That's how we get all the nice structured mesh, 3D finite volume framework, and portability and extreme GPU scalability. We also have the sundials time integration suite implemented into MagNex so that we can have a multi-fidelity selection of, if we would like our simulation to be faster or more accurate, then we can select different orders of sundial integrator. We later implemented the ML surrogates to replace the FFT calculation. And that's where we're still having problem. We're still actively working on this, so we welcome any suggestions or solutions to solve this problem. So I will introduce that later. All right, so I'll skip this because I talked about it. Then let's come to the validation. So we have our equation defined, and we have our model set up. Now I would like to give you some validation against standard problems that people use in this community. One of the good part of micromagnetic community is that they have a set of well-defined standard problem. So whenever people build their own micromagnetic solver, if you show that, hey, I validated against 4 standard problems, people will start trusting you, right? If we do not validate against the standard problem, then that means we still have a long way to go. Okay, so standard problem 2, 3, and 4 are listed here. Of course, we have standard problem 1, but for the limit of space, I will present the second, third, and fourth. The second problem is the resonance magnetization in a magnetic slab as a function of system dimension. So basically, we have a slab of magnetic material, and we apply magnetic field onto the material, and we sweep the magnitude of the magnetic material. We measure the magnetization that's induced by the external bias. And we change it. We change the size of the material. So we get a curve of the remnant magnetization, and it's matching not only the theoretical result, but also other published magnetic solver. The third standard problem is a stable flow and it's actually flower, stable flower and vortex states. By flower, we mean that if you look at the vector of the magnetization, it's pointing upward like a flower bloom. And then there's a vortex states, meaning that the tip of the magnetization is forming a vortex shape, right? So these are 2 different topologies of magnetization, but they come from the same material. The only difference that we made for these 2 states are the initialization. So the solving of LOG equation is trying to find the energy minimum state of the material. And it really depends on where we initialize the material, right? So if we initialize it around local minimum 1, then the relaxation will bring us to local minimum 1. If we initialize it around local minimum 2, then the relaxation will bring us there, right? So these 2 states are coming from 2 different initialization, but the solving process are the same. So it brought us to these 2 different states. And again, this is validated, and people would expect, and they did observe the same flower and vortex states. The fourth one is more complicated. So other than just relaxation, we actually put active magnetic field, the external magnetic field that is defined by the user. So let me, okay. So this is, sorry, the animation is not playing well, but basically what I want to show is we have a magnetic thin film, and we initialize it to some magnetization state. We remove the magnetic field, and we let the system to relax to stable state. After it relaxes to stable state, we apply magnetic field as a function of time. And then we record what mx, my, and mz look like as a function of time, and we compare it against theory and other solver. So again, we see very good match. So after the demonstration of the 3 standard problem, we went ahead and demonstrate 2 more advanced problem with a type of new physics. It's called Dzyaloshinskii-Moriya interaction. This is one of our new contribution on top of very standard micromagnetic simulators. So DMI, Dzyaloshinskii-Moriya, is nothing more than just some curl product between M and its own effective magnetic field. Here we're showing again that, so this is a steady state of two vortex topology coming from the DMA coupling with other coupling. So apologies that the animation is not showing up properly, but basically this is what we call skyrmion. I'm not sure if this word ring the bell in some of you, but skyrmions are one of the most promising technologies that allow us to do microcontrol of the magnetic texture. It is very promising for computing applications like reservoir computing, neuromorphic computing, and probabilistic computing. So we implemented the physics here and validate the DMI interaction and showcased the skyrmion as a function of time. Okay, so next, I would like to show our scalability study. We have the weak study, the weak scaling, which is time simulation time per time step. As you can see, up to hundreds of parameter GPU, the simulation efficiency is pretty flat. And this is a strong scaling where we have, this is also the weak scaling, my bad. This is a weak scaling, both of these are weak scaling, but the right has the FFT demagnetization calculation. So without the FFT, the weak scaling has been pretty perfect, flat, right? But with the FFT calculation, scaling is not that good. You can see some linear trend increase in the time per time step. So that is motivating us to see if we can have some alternative strategy to replace the FFT calculation, but we can still do the demagnetization calculation. So we went ahead and replace part of the FFT, part of the LG solving with machine learning. Okay. So before I get that, let me just very quickly show you the sundials integration that we have. We know sundials, that's a suite for nonlinear and differential linear algebraic equation solver. So we implemented that with the multi-rate infinitesimal MRI schemes. And this is how we are using that advanced time integration with sundials. We have demonstrated up to 3 times speed up over 4th order Runge-Kutta integrator. So that has been working pretty well for the stencil calculations. That is everything except for the FFT, right? But for the FFT, that's still the performance killer. So we were implementing the machine learning module into the MagNex. Here is just an overview of which part of the MagNex calculation that we replace with machine learning. As I showed, the stencil calculation, including the DMI, exchange, and anisotropy, are pretty fast because they're based on AMReX stencil calculation. But then the last part, which is marked as pink color here, that is based on the FFT. That is slow. So we replace this part with FNO, Fourier neural operator, because of the similarity between Fourier transform and the solving of the Green's function of the kernel calculation. And then so this is a hybrid modeling system, meaning that we're still doing numerical modeling for the other terms, but we're using neural network, which is FNO, to do the FFT, to do the demagnetization, which is one of the key terms here. And here is the demonstration for the standard problem 4 with FFT part replaced by FNO. So what we did is we generated 1,000 training set with different H field. So remember I was talking about the difference between problem 4 and the other problems. The difference is that we have user-defined magnetic field applied on the magnetic material. So here other than just one set of magnetic field, we have 1,000 sets of the magnetic field, and we generate the time sequence of magnetization for each of this magnetic field set. And again, this is the demonstration here. I'm just showing two demonstrations because of the space limit, but we're getting pretty good match between the numerical only and with FNO, so the hybrid modeling. So field 1, we see almost perfect match for all three magnetization components, and for field 2, almost perfect match with some acceptable discrepancy. We also went ahead and see if we can demonstrate the same hybrid modeling capability with Skyrmion. So same 1,000, actually 200 samples for this case, because this simulation is taking more computing resources. And here I'm showing the magnetization distribution. This is a top view of the thin film that we simulated. So we're seeing pretty good match here. Okay, and this is the last page of this presentation here. We built a MagNex simulator based off AMReX, and we replaced the most time-consuming part with FNO. But the problem here is still, first, for some of the applications, we're not seeing perfect match. And this is okay for for visualization purpose, but when it comes to quantitative performance and when it comes to more complicated device simulation, this becomes an issue. So we're actively looking for more accurate neural network beyond FNO. And the second challenge we're having is, see, we're generating 1,000 or hundreds of samples of data sets, right? And that gives us storage problems. So we're looking for workflows that can make the training more more interactive on the fly so that we can save space. All right, so this concludes my first talk. Welcome any questions or comments. Yeah.
So I'm assuming that every time you set up a new case, you have to do some training, right? For that particular case?
No, actually, the training is done after the entire time sequence was generated. And then the inference just happens every time step. We don't retrain at every time step.
But let's say if I change some configuration of the simulation, some
Yes.
real world problem.
Yes.
You'll have to fine tune the model every time.
Yes.
You are doing a different simulation.
Yes.
So do you have a strategy of, like, let's say, creating, like, having a model that is trained over time, then that sort of becomes a universal model for general class of problems, or
a foundation model? Not really. Yeah. I was thinking about it. Foundation model. Okay, so you will run into severe out of distribution problem if you treat it as a universal model. The fortunate part is that we're just dealing with one equation, which is LOG. So there's enough similarity between case and case. But then if I change material property, of course there will be some problem, but that's okay. But mainly the worst problem here that generate out of distribution is the enabling and disabling of this coupling of this H terms. So for one model, I may not need anisotropy. I may just need the other three terms. And then I train my model without anisotropy. For the next problem, it comes back. So how could I deal with this discrepancy, right? So I do not think a foundation model is possible at this stage with the current ML technology. But in the future, maybe. Yeah.
thank you.
Mm-hmm. Yeah.
I was looking at the AMReX microelectronics GitHub for the organization.
Mm-hmm.
And personally, I was familiar with, for example, I knew about Artemis, the code based on
Mm-hmm. Mm-hmm.
So I just wanted to ask, like, I see a lot of codes here. Do these codes have anything in common besides being based on AMReX? That could be like shared modules, shared functionalities.
That's a really good question.
Like really parallel, independent codes that don't intersect beyond being based on AMReX.
So unifying them as one framework is our ultimate goal. We're working toward that. Currently, they're independent from each other. So if you're on the GitHub page, you might see two packages. One is µMAG that I'm talking about. The other is called FerroX. Okay, so µMAG is for ferromagnetic material. FerroX is for ferroelectric material. They share very similar energy landscape. They share similar features, but they're talking about different order parameter. µMAG is magnetization, FerroX is polarization, right? But there is a third category of material called multiferroic material that has both polarization and magnetization in one piece of material. So that requires us to solve polarization and magnetization in one simulation. So that connects µMAG and FerroX. That's our goal. But we just haven't done that. Yeah. Okay. Yeah. I'll talk about Artemis in my next talk. Yeah.